Welcome to the Science Program. My name's Jeff. This is a kind of knowledge experiment. The Science Program is a series of educational video programs intended to expand knowledge and help improve understanding of a variety of topics by gathering information, establishing structure and context, and achieving clarity. Guests are experts in their field. The intended audience includes fellow experts as well as people who may be interested in the topic. Basic understanding is first established and additional information is provided to broaden knowledge. Key science indicators are proposed. These are a set of metrics that are intended to eventually be broadly agreed upon and that are consistent, recognizable, and measurable. The word program has dual meaning as well. In addition to a video program, the goal over time is to refine these metrics and establish a common understanding among experts and those interested in the topic. I'm very excited to welcome my guest, Dr. Anthony Ingraffea, Professor Emeritus of Civil and Environmental Engineering at Cornell University and member of Earthworks Board of Directors. Dr. Ingraffea is an expert on complex fracturing processes and rock mechanics. He has served as principal investigator on over $37 million in research and development projects, has authored numerous publications, was named among People Who Matter in Time magazine, as well as achieving numerous other awards and honors, including notable projects that you see there on the screen. It's been an absolute pleasure to work with Dr. Ingraffea on this episode of the Science Program, and Dr. Ingraffea has assured me it's fine to call him Tony. So with that, I welcome my friend Tony to this episode of the Science Program. Hello, Tony.
Hello, Jeff. I agree. We've been working very hard on this to bring the best possible show to your audience. This is a year in the making, and tonight's the night. So thank you very much for the opportunity.
Absolutely. I'm so excited that you decided to be a part of it here, and I think that the one thing that we can probably agree on is, as we've gone through this process, I know I've learned a lot. And I hope that you're excited to provide a lot of this detail in a new and different context that maybe the audience can appreciate, especially with such a complex topic as this.
Good. Let's do it.
All right, Tony. So if you could take us through an overview of what unconventional development of oil and gas wells is really all about.
Sure, Jeff. First of all, let me make sure that your listeners understand what an unconventional means. Conventional wells have been drilled for over 150 years. Unconventional wells, as they're currently defined, have only been drilled for about 20 years. Fracking does not mean unconventional. Fracking is not new. Unconventional is new. More specifically, unconventional in shale is what's new. So that's one thing I want to make sure your listeners understand. I'm not talking about fracking. I'm talking about unconventional development of oil and gas from shale formations. That is relatively new. All stimulation methods, and fracking is a stimulation method, are designed to increase the productivity of a well. And so in shale, it's very, very difficult to get natural gas and oil. If it was easy, they would have been doing it decades ago, but they've only been doing it for the last 2 decades. It's very difficult. It requires a very special form of fracking. And when that special form of fracking is combined with things called directional drilling, high volumes, tremendous amounts of fluid injection, and clustered multi-well pads, these are all new technologies that have been developed in the last 20 years specifically to get oil and gas out of shale. The specific point I want to make tonight about unconventional wells, oil and gas, is that they came at the worst possible time from the point of view of climate change. Because what they've done is extended the fossil fuel era. As noted on the slide that we're on, natural gas is mostly methane, and when you burn it, it creates carbon dioxide. When you don't burn it and it escapes into the atmosphere, as it inevitably does when you're drilling and producing from a shale gas or shale oil well, that methane itself becomes even a more potent greenhouse gas than CO2. So summary on this slide is unconventional tonight means shale. Shale means oil and gas. It means the latest and greatest, depending upon your point of view, the latest and not so greatest, because what we've done is effectively elongated the fossil fuel era for another 2 decades at the worst possible time. So let's go to the next slide and expand on that a little bit so that people understand the timeline. So,
and it's worth noting on this slide, fracking, been around forever. Unconventional is a whole suite of chemicals and techniques that are relatively new. And That's what we're going to get into here to really get into the details.
Exactly. So as this timeline shows, oil and gas drilling has been around since the mid 1800s. Conventionals since that time. Unconventionals research was done in the late 80s, early 90s. I was involved in that, some preliminary research. It wasn't until the late 1990s that one company in Texas figured out the magic sauce. What combination of technologies were necessary to get oil and gas out of shale. And by about 2000, the barn door was opened, and in various places around the country, Texas, Pennsylvania, West Virginia, Arkansas, Louisiana, North Dakota, Colorado, all of these places have shale formations, and they have been pounded for the last 20 years. So all of the improvement, it's important for your listeners to understand this, all of the vast improvement, increase in producing natural gas and oil in the United States has come from shale. Conventional wells were literally going dry. We were already importing natural gas 20 years ago. We were importing most of our oil 20 years ago. Now we're exporting natural gas, and we're importing only about half the oil we were importing. That's the good news if you're a fossil fuel fan. If you're a climate change worrier, like you should be, that's really bad news because all that oil and gas is getting burned or getting leaked into the atmosphere. And what we've done in the last 20 years is made the fossil fuel industry very happy and their shareholders, and we made climate change much worse.
And I think the big takeaway from slide number 9 here is these conventional techniques have more or less been exhausted, right? And we're now reaching an era on this timeline where, because those traditional sources have been exhausted, there's additional gas that usually was not obtainable. But that's really kind of tipped the scale because it's almost an apples to oranges in terms of the complexity and effort to get the gas out of the ground, but also some of the byproducts that maybe are not good or may not be desirable.
Exactly. So you don't get something for nothing. They figured out how to get oil and gas out of shale. So if you go to the next slide, actually the next 2 slides, they're pictographs. They're industry-generated cartoons that try to show the difference between unconventional and conventional. So they're putting in the pictures all the words I just used in the last 5 minutes. So we shouldn't spend too much time on these slides, but obviously your listeners are going to get a chance to study them and listen to what I've said about them. But as you just pointed out, we were running out of conventionally produced oil and gas. We were on our way to hopefully converting to a green renewable energy economy. And literally at the last moment, and at the worst possible moment from a climate change point of view, they figured out how to unlock shale. The keys to the kingdom were opened up.
And it's also worth noting that fracking, been around for a while. Unconventional oil and gas development, literally apples and oranges in many important contexts, right? Which we'll continue to explore here.
Exactly.
Slide 12 we're on here. What are we looking at here in terms of the physical mechanics of extracting this gas in this unconventional way?
Well, I'm looking at slide 11 right now. So what they're trying to show here is if you're drilling into a gas-rich shale, that's the gray gas-rich shale indicated there, you're no longer drilling straight down as you would in a conventional well. You see a conventional well to the left of that drawing, where you're just drilling straight down into a pocket of gas or a pocket of oil. When you're drilling in shale, there are no pockets. The gas and oil are distributed throughout the shale. Think of the shale as a big black sponge. And what you want to do is squeeze as much of that sponge as you can. So you're going to drill down to it and then drill along it, into it, as you can see from the deviated well. That's what the industry calls a deviated well. It's directionally drilled so that most of the well is in the shale. It's not just touching it, it's in it. And the current generation of shale gas and oil wells are such that the length of the well, the total length of the well from the surface to the very end of the well, is typically now 3 or 4 miles. You might only have to go down a mile to get to the shale, but then you're going to drill another 1 to 3 miles through along the shale. That means you're getting as much of your well in that big sponge of shale as possible. What that means...
And it really is helpful to explain it like a sponge, because the gas is molecularly attached
Yes.
to the sediment and that tightly compacted rock.
Think of a sponge.
And so if people can imagine it being like basically a solid rock that's sponge-like,
Yeah.
once that's fractured, the gas can be released.
It's not soft like a sponge, but the image I want your listeners to have is when you're holding a sponge in your hand, you see a lot of spaces, open spaces. Those are called pores.
Right.
Okay, in shale, those pores are submicroscopic. You can't see them with the naked eye. You need a very powerful microscope to see them. But all those submicroscopic pores hold molecules of gas and oil. So to get a well to be productive, you have to have your well come in contact with literally billions, trillions of those little pores. Hence, your well is going to be miles long. So the sponge analogy sort of works, as long as your listeners don't think that shale is soft. It's not. You're not squeezing.
Exactly.
You're just getting your well to contact and intersect as many of those pore spaces as possible.
And slide 12 goes into a bit more detail here as far as the illustration, right? That does a good job of showing that tight formation at the bottom there.
Yes.
And how that shale must be fractured to get those microscopic pieces of gas off of the rock there.
Yeah, and slide 12 also starts talking about certain terminology that's associated with all wells. You have the well bore, which is the hole that's drilled from the surface down to your source. In this case, your source is shale. And it talks about well casing. So when you drill a hole in the earth, in general, that hole isn't going to stay open by itself. It'll typically want to collapse on itself, even if it's in solid rock. So you have to put into that hole steel pipe called casing. That steel pipe serves to stabilize the well. It serves as a pathway for the oil and gas to get from shale, in this case, up to the surface. But when you drill a hole and you insert steel pipe in it, the hole you drill has to be larger diameter than the steel pipe. Otherwise, you can't get the pipe in. So that creates a space between the outside of the casing, the steel pipe, and the rock. And that space has to be filled. In most cases, it's filled with cement. The same kind of cement that they use to make sidewalks. It's not concrete, it's just cement, powdered cement and water with some additives. It's very cheap, goes down as a liquid, and after some time it solidifies and it forms a gasket. It tries to seal the gap between the steel casing and the rock, because you don't want what's down there coming up outside your steel casing. You only want it coming up inside the steel casing. But best laid plans, these are man-made structures built underground where we really can't see what's going on. So things don't always work out as designed. We'll get to that later.
I was going to say these well casings and technologies to seal are perfect, right? They're impervious to any. I'm just joking.
Yeah, no, they're not perfect. and we'll see what happens when they're imperfect later on. We'll actually show some videos of what happens.
Absolutely.
when wells leak, and wells leak.
So just looking at slide 12 there, top to bottom, more or less, that vertical structure is similar or the same for traditional fracking.
Absolutely.
But when you get down, or is it quite different?
Yep. All the vertical part is traditional. It's the same. It's only when you get down to the shale and you make that bend, and you push your well out for a couple miles through the shale, that's where things become unconventional.
Gotcha. So moving on to slide 13, this kind of just shows the broader systems involved with getting this gas out of the ground, and a real quick synopsis of what we're looking at here.
Yeah, the reason why we put this picture in is because it shows what they call the whole product stream, life cycle. So on the left, you have what are called well pads. That's where you drill your well, you stimulate your well, in this case using fracking, and you produce your oil and gas. But obviously it has to get to market. And it can only go through pipelines. So you have to put what are called gathering pipelines to connect all of the wells to the place it has to go in order to continue its process downstream. So let's talk about gas for a minute, because this particular slide pertains to gas. So you have gas coming through gathering lines from all your wells, it has to go to a compressor station. A compressor station is a facility, a mechanical facility where very powerful pumps take the gas that's coming from the wells under relatively low pressure and increase the pressure so it can go into transmission pipelines. Those are the ones that go all across the country. They're typically large diameter, 3 or 4 feet. They're buried 3 or 4 feet underground. They can be thousands of miles long. Before there was unconventional natural gas, when somebody in my hometown wanted to cook a hamburger in their kitchen, they were cooking with natural gas that was coming from the Gulf of Mexico.
Oh, wow.
So there was a big transmission line or series of transmission lines that came from the Gulf of Mexico to the northeastern United States, to Ohio, and to New York. Nowadays, the gas is coming out of the Marcellus. You're getting gas in Ohio that's coming directly from Ohio, and we're getting gas in New York that's coming directly from Pennsylvania. But to get the gas into those transmission lines, you have to increase the pressure by a factor of 3 or 4 in some cases. And I'm going to show a video later of what a compressor station looks like in operation. The next thing that happens is the gas has to go to a processing plant because the gas isn't pure methane. What you're burning on your cook stove is close to being pure methane, CH4, 1 carbon atom, 4 hydrogen atoms, methane. But when it comes out of the ground, it's methane, ethane, propane, butane, benzene, xylene. There's all kinds of things, all the way up to oil. And you have to go to a processing plant and separate all those components of the natural gas out so that you can get liquids like butane or oil and take those by tank car to where they're going to be used. The gas then goes farther downstream, and it either goes into a storage facility or it goes directly to market. The market might be here in the U.S. or it might be nowadays, LNG, liquefied natural gas. You take the natural gas, which at standard temperature and pressure is a gas, and if you chill it and pressurize it, it becomes a liquid. You then put it in tanker ships and you transport it around the world. So the end use could be heating your home. The end use could be drying your clothes. The end use could be heating the hot water in your house. The end use could be cooking food in your kitchen. It could be creating electricity. It could be going to a cracker plant where it's broken down into things that are used to make plastics, for example. Those are all the uses of natural gas.
And some of the dynamics that change, and I like your example of the Gulf of Mexico as being a source in the 70s. Where I grew up, we had a massive gas pipeline that went through the woods near where we lived. And I remember they would come through and spray pesticides. That's probably a whole separate topic. But so let me make sure I understand what you're saying. So those traditional pipelines, those require to be under higher pressure as well, those long haul pipelines?
Yes. Typically, for those in your audience who understand pressure, the gathering lines that are coming from individual wells and going to the compressor stations are small diameter, typically 3 to 6 inches in diameter, and the pressure in them is only a few hundred pounds per square inch. The transmission lines are typically 3 to 4 feet in diameter, and the pressure in them is between 1 and 2,000 pounds per square inch. So if you want to know what 2,000 pounds per square inch is, hold out your finger and put your car on it. Put your car in your fingertip.
Fantastic.
That's 2,000 pounds per square inch. So
how do the gaskets and all the infrastructure then? I imagine there's some advanced engineering to make sure those things are in good use, but are there situations where some of these long haul pipelines are maybe being pushed to excess because they were designed for an older system?
Yes, and even new pipelines, if they're not well designed, can have problems. There have been 3 situations in the last 2 years, one of them in Ohio, where a brand new natural gas transmission pipeline failed. And when it fails, remember, it's carrying very high pressure gas, very high volumes. It explodes. Some viewers probably remember seeing that on TV, these big fireballs.
Yeah.
And in those cases, the pipelines were poorly designed. They were subject to unforeseen earth movements, and they failed. Older pipelines can also fail because they can corrode and they can crack. Pipelines have to be inspected periodically. There's federal regulations that require all transmission pipelines to be inspected using advanced technology. But, as you said before, these are man-made objects. If a 737 Gen 8, okay, whatever they call it, if that one, those things can fall out of the sky, brand new, then you shouldn't be surprised when gas pipelines, whether they're new or old, also have problems. Anything that
looking at slide 13, then the pipelines themselves, those long haul pipelines, that seems like a delta, right, between traditional fracking and natural gas distribution and this increased pressure now required to transport those. But also the cracker plant. I mean, those were likely located closer to the source of the original extraction, right? Now these things are maybe showing up in areas that they weren't back in the 70s.
They're showing up in your backyard, Jeff.
And that's what I'm hearing from some friends, especially in Western Pennsylvania.
Yes.
Where these things are starting to show up. Doesn't make any sense to build them far away. You want to build them close to the source. So that's another delta.
Yep. Let's move on. Let's go to slide 14. Again, I'm trying to summarize here. I'm trying to summarize what the differences are between conventional and unconventional. And if you just take a cold, cruel look at it from a business point of view, and you compare conventional and unconventional, their advantages and disadvantages. So conventional, the advantage is you got methods that have been used for over 100 years. There's less contamination. It's easier to seal the wells. You can limit the contamination easier. The disadvantage is that you're running out of supply.
Right.
The advantage of unconventional wells is it's a new source, a huge source of gas and oil. It's not infinite. It's not forever. We will run out of unconventional oil and gas in my lifetime. I'm 72 years old. I think I got about another 10 or 15 years to go. We will run out of it in this country in that period of time. So
wow.
We're really, pardon the pun, we're dredging the bottom of the barrel here.
Literally.
Shale was the last, and once you get the oil and gas out of shale, there is no more, because shale is the source of all oil and gas. It's where it comes from.
Yeah, and the economics is fascinating too, because there's a surplus on the market.
Prices have plummeted.
So there's maybe some improvements for local communities, but what's weird about that is that extra supply comes on the market, prices drop. There's then preventative aspects to drilling new wells because the cost-benefit analysis kind of falls apart. But also the true economic cost, not quite as transparent when you look at perhaps impacts on infrastructure and other subsidies and taxes that maybe need to go into local infrastructure, right? I mean, all those things are what we're trying to explore with this whole discussion.
Yes, and two other factors here while we're talking about the so-called disadvantages of unconventional. You're correct. The true total economic cost is not transparent. You have externalized costs because you have local pollution, you have local human health effects, and you have the cost of climate change. You have short-term contamination risks and near-term because wells leak. And if they leak, the leakage can get into an underground source of drinking water and kill somebody's water supply. If they leak into the atmosphere, they're leaking methane, which is a greenhouse gas that's about 100 times more potent than carbon dioxide over about a 20-year period.
Yep.
So I'm emphasizing, I'm saying the same thing over again for emphasis. If we had not entered into the unconventional oil and gas era, you and I wouldn't be having this conversation. We'd be having a conversation along the lines of, gee, Tony, gee, Jeff, how far along are we now in transitioning to truly green renewable energy?
Right.
We wouldn't have 2 Teslas in my hometown. I own one of them. There'd be 2,000 of them. Your home would be completely electric. And the electricity would be coming from windmills and from solar fields and from hydro. But we didn't.
And a lot of the market forces would drive innovation and incentive to maybe not. It's a whole different topic, and I don't want to go off the rails too much on this, and we'll get into some of these metrics, but that's what I'm excited about with this particular science program is looking at the bigger model. So like, for example, if fuel prices did increase because of limited supply, maybe there would be incentives to live closer to where people work or more regional acquisition of goods and services so that those costs, that demand would drop, and we can kind of retool the broader landscape, which is what I want to continue to explore here as we go through slide 15 and then getting into the first detail here about the geologic considerations over time.
Yeah, let's focus, for example, on one of the things we're calling short-term contamination risk. This is one of the costs that isn't included when you get your bill for gas, and you notice that you're paying less for gas than you were 10 years ago. What's not on that bill is the cost incurred by your neighbors who have lost their water supply.
Right.
Okay, so how does a gas well contaminate a water supply? So this slide is supposed to show the vertical part of a well, the beginning of the turning of the well down into the target producing zone, which is that gray shale at the bottom of the picture. And that also shows, in this case, 3 layers of casing, 3 steel pipes, one inside another. The innermost is a production casing, then there's a surface casing, and then there's a conductor casing. And you can see that some of the gray gap between the casing and the rock is filled with cement, also shown as gray. Mm-hmm. Those little red dots are supposed to be methane molecules. And if the well was constructed correctly, then those methane molecules that are in other layers of shale, because there's not just one layer of shale or one layer of gas-bearing rock on the way down, there are multiple ones. You don't want the gas coming from the ones that you're not using for production to get to the surface. So this particular picture shows everything working fine. Those red dots are confined. They can't get to the surface. Good, wonderful.
And keeping an eye on that freshwater aquifer as we continue now to slide 17.
You want to keep your eye on, because if we go to the next slide, what happens if the cement, and you'll see that blow up, that little black circular blow up, you'll see casing, which is steel, you see cement, which is cement, and then you see formation, which is rock. And in this case, the cement has not bonded to the rock. There's a gap. That's called channeling. Right. If that gap exists, then some of those red dots, the methane molecules, can get into the gap between the production casing and the surface casing. And it can go all the way up to the surface. And at the surface, now you see that red arrow? That's a pressure buildup, a gas pressure buildup. That gas pressure buildup can now force gas into the freshwater aquifer. You now have a contaminated aquifer.
Yep.
Forever.
And then looking now, so slide 18 takes us.
That aquifer is going to be contaminated.
As I say, sorry, back to slide 17. So if anyone's ever picked up a piece of concrete, like if you look at your driveway that's paved or any kind of sidewalk, if you ever see one of those things break off and you pick up the unfinished side, that's kind of what we're describing here, where there's rocks and inconsistencies in the surface material. It's difficult to keep that thickness completely consistent, right? In that cement layer.
Yep. And there are
so then slide 18 is just another way for. Oh, I'm sorry. Go ahead, Tony.
Yeah. So Jeff, we don't have time tonight for me to go into the many, many ways that wells can fail. That picture I just showed you is one phenomenon called channeling, and there are various causes for channeling. If we go to the next slide, in this case, the cement is okay, but the casing itself has failed. It's steel. It's subject to corrosion. It's subject to cracking. It's subject to mishandling. And so if the casing fails, then any of the methane that's coming up inside the casing, supposedly going to production, can now leak into the freshwater aquifer.
Right.
So there's another failure mode. We go to the next slide. Insufficient cement coverage. How do you know that every place you wanted there to be cement to act as a gasket got to where it was supposed to go? It's thousands of feet underground. You can't see it. Now, the industry has various advanced physical tools, physics-based tools, temperature, sound, radiation-based tools to try to determine whether the design of the well was actually executed correctly. But it isn't always executed correctly. And if they find out it isn't, the way they usually find out is the well leaks.
Right.
And if it leaks, and then you have a possibility of freshwater aquifer contamination. Then you have the onus of going back and trying to repair the well. That
Right.
costs money, big bucks. You have to take the well out of production. You have to bring back the organizations that first drilled the well and completed the well and hope that you can fix it. And sometimes you can, and sometimes you can't.
Looking at these series of slides, I'm looking at slide 19 now. There's another aspect here, which is the geologic force of the Earth itself. The fact that this Earth is not 100% static over the course of years. There's movement within the Earth's crust. And that's just another variable that 100 years, 50 years, some longer duration, there's likely going to be some horizontal force that could continue to exert pressure and perhaps cause additional failures.
Exactly. And so your listeners should be thinking, wait, we're drilling thousands of new wells every year. There have been 2-3 million wells drilled in the United States since the 1800s. Hundreds of thousands of those wells are lost. We don't know where they are. They're abandoned. Some of them, most of the lost ones are orphaned. That means there is no longer a corporate responsible party for them. And every one of those wells is a potential leak path. You created a human hole in the ground that goes from the surface down to a source of hydrocarbons. And if that well isn't cared for, isn't maintained forever, then at some point between now and forever, it can become a leaker.
Right. And that's a good segue then into impacts as we look at really when these things are drilled, the lifespan of the well, to your point, where it's an active producing well is one time frame. There's a whole host of longer term impacts. And some of these variables of economics, environment, again, it's a fascinating segue because that time horizon isn't just when the well is active. So just a real quick here on slide 21, why does any of this matter, right? We're looking at the economics as well as the environment as two major categories. And who's ultimately impacted?
You and me and our kids.
Exactly.
And our grandkids and their kids. Wells that were drilled in the late 1800s are still being discovered. They were lost. They're still being discovered today all over the country. Wells drilled over 150 years ago that are leaking, and they've been leaking for decades. And they now have become what are called wards of the state. The state is now responsible for finding those wells and hopefully stopping the leaks. Who pays for that?
Right.
Taxpayers.
And what I was going to say, it's obviously communities where the wells are present. That's a pretty obvious thing. You can see these wells popping up in individual communities where fracking wastewater is stored. I'm always mindful of the fact that our drinking water supply comes from a river. And if there's fracking wastewater being transported or otherwise stored, there could be impacts, even though there's not fracking in my neighborhood. People that live near and far from wells. And storage facilities, right? I mean, there's any impact isn't necessarily where these things are happening. In other words, it doesn't have to be in your backyard to suddenly wind up being in your backyard. And that last bullet point, the climate change aspect, the fact that we're pumping in greenhouse gases, that spectrum of impact, whether you see the physical well or you happen to walk outside and need the climate for things like food, solid ground, that whole spectrum are potential impact categories, right?
Absolutely. When you get to climate change, everybody's in the backyard.
Exactly. And looking at that well pad there,
everybody's downstream.
Well, and exactly. And again, that picture on this slide 21 is, I think, fascinating because you would look at that and say, oh, okay, people maybe within the visible distance of this would be impacted. But these longer considerations, the fact that, and we'll get into the discussion about the underground aquifers as well. But there's a water table underneath that place. There's obviously the atmosphere for some of the off-gassing and things that go on for the mining process. It's important to realize just because you don't see it doesn't mean some of these metrics that we're going to talk about won't show up and impact you at some point. Slide 22 is kind of another very physical reality of just how extensive this is. Correct.
So we're still looking at slide 21. This is the first time we've shown an actual photograph of a drill pad. That's the area on the left. It's kind of hard to see, but there are 1, 2, 3, 4, 5. Looks like that's an 8-well pad. 8 wells were drilled from that pad. It looks like 3 of them are already in production. Up on the right is not a swimming hole. It's a man-made retention pond, and there's one associated usually with a well pad or a group of well pads, and it's where they store the water that's necessary for the fracking process. And I think you can understand the scale here. You can see trucks that are very, very small. So that's a man-made lake for all practical purposes. It has a few 100 million gallons of water in it. And each one of those wells nowadays requires between 10 and 20 million gallons of water for fracking. And much of that, in some cases, most of that, once it completes its job of fracking underground, comes back to the surface, and it's no longer water. It's wastewater. And it has to be disposed of. It has to be captured, has to be transported, and it has to be disposed of. Otherwise, it becomes an environmental hazard. So go to the next slide. And what you saw on the previous slide was one pad. But if you see what's going on in unconventional natural gas, whether you're in Texas on the left or in Pennsylvania on the right, you have to have a pad everywhere that you possibly can, because there is gas and oil everywhere in the shale. You put as many pads as you can under constraints of landowner leasing, under constraints of you can't put one inside of a school or a hospital, but you can put one in the parking lot of a school or a hospital. And on the left, what you see is an aerial view of an area just west of Dallas-Fort Worth. Every one of the white dots, you can see a lot of white dots there. Every one of those white dots is a drill pad with multiple wells. And the scale is 1 kilometer. That arrow down there is a 1 kilometer distance. And you can see that pads are typically about 1 kilometer apart, less than a mile apart. So, and in between, they have people living. They're residential developments. On the right, it's easier to see. Every black dot is a drill pad. The colors just indicate different companies. And this was 2013, 6 years ago in Bradford County. The number of wells in that county now probably has doubled since then. So look at all the black dots multiplied by 2. So we call unconventional spatially intense, because you have to drill as many wells as you can, because you have oil and gas everywhere you want to drill everywhere. So that makes the whole process spatially intense. It's invasive. Most states, in fact, I think right now there's only one state in the United States where zoning, traditional zoning rules, trump oil and gas regulations.
Only one?
New York. So in your state of Ohio, if a company says we want to drill a gas well in a residential zone, your community probably has zoning, right? If a company comes in and says the people who own the gas on this property want to sell the gas to us, we want to drill on that property, it's in a residential zone. Zoning has nothing to say about it. They can drill there. Do you hear what I said?
Well, and I was going to say, yeah, and looking at the Google Earth one especially, I mean, a picture says 1,000 words. Yeah. Each one of those little tan dots is a well pad.
I'm not lying here. That's just the way life is.
I mean,
oil and gas
now
rules.
Looking at
rules.
Looking at slide 23, this is the Marcellus wells drilled in Pennsylvania.
Yep.
We got data up through 2017. I'm not sure if the 2018 numbers have come out yet or not, but what are we looking at here? I see some increases for sure. Fascinating decrease, I guess, in the number of new wells, 2015 and 2016. That correlates to maybe oversupply in the market a bit?
Yeah, there was the market crashed in 2015, 2016. Both oil and gas crashed. So there was a big shakeout. Hundreds of companies went bankrupt. Over 100,000 oil and gas workers lost their jobs. Oil and gas is boom bust. It's subject to the vagaries of international energy economics. So when the U.S. started producing a lot of oil from shale, they flooded the market. And so the price dropped. The price of oil went from a high of about $150 a barrel to as low as $28 a barrel.
Wow.
The reaction was that other countries didn't like what we were doing. They don't have shale. Not many of them do, and not many of them are producing from it. Only two that I know of in very small quantities. And so those countries responded. So to get the price of oil back up, they cut back their production to drive the price back up. Okay? And then it got into a vicious cycle because the oil price had dropped so precipitously. It's much cheaper for Saudi Arabia to produce a barrel of oil than for North Dakota to produce a barrel of oil by a factor of about 5. And so when the price plummeted, shale gas and shale oil companies went out of business. They stopped producing. So that's what you're seeing reflected here, where the rate of increase of drilling in Pennsylvania dropped off when they had that bust cycle. Now they're back in a boom cycle. So
that maximum full build out of greater than 50,000, that's the maximum build out for the state of Pennsylvania alone.
Pennsylvania. That's about what most experts are saying. If they want to drill Pennsylvania to death, literally and figuratively, if they want to get as much oil and gas out of the Marcellus as possible in Pennsylvania, it will take about 50,000 wells. So they're only about a fifth of the way. They got a little bit over 11,500 wells now in early 2019. So they're about a fifth of the way. So all the impacts that we're seeing in Pennsylvania, multiplied by 4 or 5. But don't worry, Jeff, I can assure you that we're never going to get to 50,000 wells, because long before we get to 50,000 wells, climate change will have overcome the economics.
Well, as well as the limitation of fresh water, I would imagine, and the wastewater disposal, that's got to be a huge correlation.
Yep.
So looking at slide 24, again, talking about impacts, how exactly are people impacted? I think this map is fascinating because this is showing where all this locked up natural gas is across the country, right?
Yep. Those are the major shale formations, some of which have seen intense drilling. In the Northeast, you have what's called the Marcellus. Down in Texas, you have where it started, the Barnett. In Arkansas, you have the Fayetteville. Louisiana, Texas, you have the Haynesville. Those are all natural gas shale producers. Then oil kicked in about 5 years later, around 2005, 2007, up in North Dakota in the Bakken, North Dakota, Montana,
that's right, yeah.
And in southern Texas in the Eagle Ford. All the other shale formations are relatively minor compared to the ones I just mentioned. But once we've exhausted the Marcellus and the Bakken and the Eagle Ford and the Haynesville and the Fayetteville and the Barnett, what's left is dregs. And after that, we sure as hell by then better be on a renewable energy economy, or the lights are going to go out and people are going to freeze in the dark.
I've often wondered about that with winter time. The fact that natural gas runs our furnace. I'm not sure about other people. I mean, that's a major component. And if you're going to conserve, I would think that you would want to allocate that natural gas for heating. In other words, if you're going to drill it and put it somewhere, store it when you need it, kind of like cutting firewood. Not throw it on the open market and just kind of hope that things are going to work themselves out.
Well, companies are now trying to export natural gas from the Marcellus and the Fayetteville and the Haynesville. They're trying to export it by liquefying it because the market bears higher prices abroad. Right now in the U.S., natural gas is selling for maybe $2.75 for 1,000 cubic feet, 10 therms. In Europe, it's selling for 3 or 4 times that. In Japan, it's selling for 4 or 5 times that. So the companies who are telling you we're going to be energy independent and we're the Saudi Arabia of natural gas are the same companies that are selling it and selling us out.
Well, and talking about how we're impacted, I mean, obviously, it turns into a vital natural resource when you talk about heating homes and other things domestically. But also what's interesting about this map here is As you consider the fact that the transportation of waste, storage of wastewater in ponds, air pollution from emissions, and drinking water contamination, there's a good slice of the country that has some of those more direct impacts, but also things far away from well sites. This slide 25, this aquifers are shown on the left, and then that same map that we looked at before is on the right. And I see a lot of aquifers on the left that overlay a lot of these major gas formations.
Yep.
And looking at two natural resources here.
You have to take a lot of water out of those aquifers to stimulate the wells. Let's go to the next two slides, and I'll emphasize that. So the next two slides are both saying the same thing. So we don't have to spend time on both. Let's just look at slide 26. It's a historical graph that shows from 2011 to about 2017 the number of millions of gallons of water necessary to produce gas from the Marcellus, that's the blue line, and from the Utica, that's the gold line. And as you can see, back in 2011, a typical well was using about 5 million gallons. By the time you get to 2017, a typical well was using 12 million gallons. And that's just the way the industry is working. They're finding out that to get more gas out, they put more water down.
That's incredible. This is for one well.
One well. 12 million gallons of water, one well.
And we just saw a slide that showed in Pennsylvania alone, well, the revised numbers are over 11,000 active wells now, right?
Take those two numbers and multiply them together, and you get billions.
Unbelievable. So slide 27, another
same thing. It's just another graphic. Just another graph that shows the same thing, a trend as you go from 2012 to 2017. Doesn't matter whether you're in these are by company. Each color is a different company. And you can see that it doesn't matter. All the companies are starting to use more and more water, starting off at 5 million gallons and going up towards 20 million, and it'll just keep going higher.
Do some companies have proprietary methods that allow them to get more with less water, more gas with less water?
Each company,
like, is there competition? And
yeah, each company thinks it has its own magic formula. They're very, very secretive, as you can imagine, with proprietary information. And they every well is a learning experience for them. They do trial and error, and eventually they move along the improvement path. So what you're seeing there is in 2010, they were drilling what are called first generation wells. Now they're drilling third generation wells. What's different? The wells are longer. The wells are longer. Yeah. They use 3 or 4 times as much water and 4 or 5 times as much sand. So what I'm not showing you here is during the stimulation process, the fracking process, you inject not just water and chemicals, you have to inject sand. The sand,
that's right.
The sand acts to prop open those pores, the cracks that you're creating between the pores. And so back in 2010, they might have been using 100 pounds of sand for every 1 foot of well. I'm holding my hands up 1 foot apart. They would have to inject about 100 pounds of sand. 2 sacks of playground sand, if you want to think about that. Go to your local supply store, buy 2 sacks of playground sand, and put those 2 sacks of sand in 1 foot of a well. By the time you get to third generation, it's 1 ton of sand. I hope what you heard. Did you hear what I just said? 2,000 pounds of sand in 1 foot of well. And the wells.
And this is all because
the wells are 15,000 feet long.
So the cost benefit analysis would, I guess, with these techniques of more water, more sand, they're able to extract more and more gas
at a higher cost.
That's fascinating. Well, and the other thing about this slide on 27 is I would think for the good of the industry, the good of the planet, like I think of technology with open source initiatives where you would openly share technology to try to just benefit. The economics fall apart pretty quickly with that concept, right? These companies are competing with each other and they don't want to give away their secrets.
Yeah, that's one of the badly kept secrets of the industry. But let's move along.
Fascinating.
We're running out of time. We got a lot more to do here yet, Jeff.
So slide 28, talking about impacts.
Yeah,
we got a house here with some stuff in the backyard.
Major impacts. There's economic benefit. There's economic cost. There's air quality. You certainly don't benefit air quality. It's only a negative. You don't benefit water quality, it's only a negative. And you don't benefit climate, it's only a negative. That's how people are impacted. They either impacted in their pocketbook, they're impacted in their water supply, they're impacted in their air supply, or they're impacted by climate.
And slide 28 also showing that zoning topic, right? These things can pop up where they need them to.
There you go.
Yep.
In most states, it varies from state to state. In most states, a company is allowed to create a drill pad and drill a well 300 feet from the nearest residence. That's the length of a football field. 300 feet.
And that's what we're seeing here, it looks like, huh?
Yeah. So,
my goodness.
Going to the next slide. We're on slide 29 now. What are the consequences of not understanding what you're doing? Well, health may be at risk from drinking contaminated water. Your local water supplies may become irreversibly contaminated. That has happened in a number of communities around the country. Air quality may be poor. So when you leak methane into the atmosphere, methane is an ozone precursor. Sunlight plus methane equals ozone. Ozone, as you know, you have kids, I have kids. Ozone is not good for the lungs of young people or aged people or sick people.
Right.
Okay. Greenhouse gas emissions. CO2 and methane are the primary greenhouse gases. You get CO2 from burning oil and gas. You get methane from mining oil and gas because it leaks into the atmosphere all along that supply chain that we talked about.
Yep.
All right. So what should we have known before we started doing this? Before we opened the barn door in 2000, what should we have known? We should have known something about all those possible health effects. We should have known something about the probability of contaminating water supplies. We should have known something about air quality degradation. We should have known something about the health effects of air quality degradation from oil and gas. And we should have been able to predict how we were going to create more greenhouse gases that were going to exacerbate climate change. We should have known that in 2000 before we started.
Yep.
But that's not the way it worked. So here we are 19 years later. And in the best database in the universe is one that my organization created and keeps monitoring. Every day we monitor all of the peer-reviewed scientific publications around the world that have influence, that are impacted by oil and gas operations, specifically unconventional oil and gas operations. If the peer-reviewed publication has anything to do with unconventional oil and gas, we find it and we cite it and we put it on a website. So your users, your viewers tonight, if they want to, can go to the website that's mentioned on this slide. And what they'll find is not 1,400 peer-reviewed publications, but as of today, 1,700.
Oh, wow.
Since we started putting this talk together over a year ago, there are 300 more publications. So
unreal. Science
is learned. We're now learning after the fact, which is back after.
Well, and the idea, this term has also crept into some of the discussions I've read. This concept of sacrifice zones, right? Where some of those peer reviews on that database, that's all fine and good. But once those metrics are exceeded, then you have a situation where you can't live there anymore.
Yep. You lose your home. So your home loses its value because it has no fresh drinking water supply. You have to move out because you and your kids become ill from ozone or from fumes. A pipeline goes through your backyard and you say, well, I don't want to run the risk. You've got pads, multiple pads within a half a mile of your house, and the lights that are on 24/7, 365, the bright lights, and the noise from drilling and the noise from fracking and the noise from the trucks are driving you nuts. So you move to Florida.
Right. Well, and so kind of wrapping up on slide 30, direct impacts, air contamination, water contamination, and global warming acceleration. Yep. The indirects, the contamination may come later as there's geologic shifts, population demand for fresh water over time. There's only so much fresh water on the planet, and there's people that need that. The true financial cost not being understood, as well as environmental damage, delayed, but perhaps permanent.
Yep.
Those are things that I think kind of shape up the next round of discussions here as we look at some of the direct examples on slide 31.
Yeah, slide 31 is a video. So you can go ahead and start that video, and I'll narrate what you're looking at. Let me know when it's going.
Yeah, it's going.
Okay, so this is a video taken by the Pennsylvania Department of Environmental Protection of a well in northeastern Pennsylvania that was leaking. We showed some slides a few minutes ago of various pathways for gases to leak outside of the well. So what you're seeing is bubbling. It looks like a hot tub. That bubbling is methane gas and other gases coming to the surface outside of the well. That gray pipe that you see is the production casing. The gas is supposed to be coming up only inside that pipe, not outside. But because the methane is coming to the surface outside, there's a high likelihood that that methane also passed through the water table.
Yep.
Let's go to the next slide.
So slide 32, what do we got here?
That's a compressor station. So tell me when the video starts.
Yep, it's going now.
Okay, that's a compressor station. We talked about compressor stations being necessary to increase the pressure of the gas coming from a well so it can go into a transmission pipeline. Periodically, the compressor stations have to blow down. So what you're seeing here is high pressure methane, natural gas, being exhausted directly into the atmosphere. In this case, for over an hour. We're not going to show an hour worth of video, but take my word for it. In this case, it was an hour of direct emission under very high pressure into the atmosphere. Blowdowns happen because of accidents in compressor stations, but also standard procedure. All compressor stations go through periodic blowdowns. That methane is getting into the atmosphere on a bright sunny day. It's an ozone precursor.
Yep.
It's a very potent greenhouse gas. Go to the next slide. Another video. Transmission pipelines, as I said, have to be inspected. They're inspected by pigs. I don't mean the animal pig. I mean a pipeline inspection gadget, PIG. It's literally an electromechanical robot that travels along the pipeline looking for corrosion and cracks and thinning. To get the pig into the pipeline, they have to exhaust the gas from the pipeline. What you're seeing here is, again, a direct emission of high pressure gas while they're emptying the pipeline in preparation for a pigging operation.
Fascinating.
All right, let's go to climate change. Let's go to slide 34. It's going to take some time to explain this one, but it's perhaps the most important slide we're going to talk about tonight.
Yes, this is very important.
So this is a graph that was taken from a very famous paper that was published in 2012. Published by a large group, a dozen or so climate scientists from around the world working on the Intergovernmental Panel on Climate Change. They put out a major report periodically that chronicles what's happening with climate change and global warming. So this graph originated in that paper without the red dots. Forget about the red dots for a minute. So horizontal axis is year, starting at 1900 and going up to 2070. And the vertical axis is global warming. The average Earth-sea temperature change, since the average temperature between 1890 and 1910.
Gotcha.
Okay, so the black squiggly line is data. It's measurement. That's what we know has happened in terms of global warming. It was, since we're starting from the average between 1890 and 1910, it starts at roughly zero. By the time you get to 2009, it's up to 0.7 degrees centigrade, 0.7.
Mm-hmm.
Then what happened back then when they wrote this paper, they did computer simulations. They did forecasting. You've appeared on the Weather Channel, right? You know about forecasting.
Oh, of course.
Yeah. So this is better than weather forecasting. It's a lot more complex. It's climate forecasting.
Right.
And they can do that. Even back in 2009, when we were ignorant and stupid, we were able to do it. And they said, let's look at a bunch of possibilities, because you can't predict the future exactly. Let's look at some possibilities. And there are 4 possibilities, each one corresponding to a colored line. There's a purple line, a red line, a blue line, and an aqua line. The purple line is what they call the reference case. They said, let's suppose in 2009, moving forward, we keep emitting into the atmosphere carbon dioxide and methane at the same rate we have been emitting it. Then the forecast is by the time we get to about 2042, we will have warmed to about 2 degrees centigrade. And by the time we get to about 2035, we're going to warm to about 1.5 degrees centigrade. Then they said, well, wait a minute. Suppose in 2009, the world all agreed, all the countries in the world agreed, we better stop emitting CO2 at the same rate. Let's start decreasing the rate at which we're emitting carbon dioxide. Then you get the red curve. The only difference is about 2 years and when you get to 2 degrees centigrade.
Wow.
And that's because most of the CO2 that's causing climate change is already there. It's been there since the beginning of the Industrial Revolution when it started. And it's there for 1,000 years. CO2 doesn't degrade very quickly. It lasts 1,000 or so years in the atmosphere.
I'm reminded of there's a lot of obvious publicity around ozone, the ozone layer disappearing, and those chemicals that would erode the ozone layer. People really need to think of CO2 and methane and other greenhouse gases as just that. It sounds like even more persistent, right, than a lot of those ozone layer destroying gases?
Well, CO2 is persistent for over 1,000 years.
Yeah.
Let's go to the aqua curve, which is the only one that's really important now for our future. This is the curve we should have been on, the aqua curve. That's the curve that corresponds to all the countries in the world agreeing in 2009 that we're going to drastically reduce the rate at which we put carbon dioxide, CO2, methane, CH4, and black carbon, BC. Black carbon is soot. It's what you see coming out of diesel exhaust, that black stuff.
Yep.
If we had started in 2009 drastically reducing, not eliminating, but drastically reducing the emission of carbon dioxide, methane, and black carbon, then the computer models back then said, well, you know what? It's highly likely we're never going to get to 2 degrees centigrade. We're going to probably get to 1.5, but we might not get to 2. All right, these are all predictions made in 2009. Well, between 2009 and now, we have 9 more years of data. Those are the red dots. So I plotted those red dots, and guess what? The models were wrong, but they were wrong in the worst possible way. They underestimated warming. We certainly did not start in 2009 on a worldwide basis to drastically reduce greenhouse gas emissions. Fast forward to 2014, we had the Paris Accords where almost all the countries in the world said we have to start, but we haven't really done much since then. So we're really on or above the reference curve, the purple curve. So in that case, the models were reasonably accurate. They're saying the reference case, which is basically we're actually worse than a reference case because we have not maintained the same rate of emissions. We've increased the rate of emissions. So if you tilt that purple curve up, it starts to look like the red dots.
And that's where I think the whole premise behind this program and the idea behind these discussions is that when people see something like this and they understand where we are relative to where we should be and the factors that contribute to very bad deviations of where we want to be, those metrics are incredibly important for people to understand because as local and state and national government entities are trying to make decisions around these policies of companies and businesses doing work in a certain way, the whole data set's got to be considered. And this chart just goes to show that this is where the rubber meets the road. Those red dots are incredibly concerning to see that far advanced of the worst case scenario from this model back when this graph was made.
One more comment here. Here's the question for your viewers. How much time do we have left to do anything? How much time do we have left? If we want to avoid 2 degrees centigrade, which everybody says is worldwide disaster. When I say everybody, I mean competent scientists around the world, biologists,
Right.
chemists, physicists, doctors, all the people who have a stake in human welfare are telling us if we get to 2 degrees centigrade, we're screwed. How much time do we have left? We have maybe 20 years. Maybe, but we have to bend the curve starting today. We have to get those red dots to start going down. Okay.
Well, let's jump into some things that maybe we can. I guess. Sorry, looking at slide 35, just another example of impact here.
This is another video that shows what I said before, an abandoned well that's leaking. It's probably been leaking for decades, and there are hundreds of thousands of those wells all across the U.S. and around the world.
Yeah.
So that's just
that time horizon is.
Let's move along to what you really want to get to here, which is the key science indicators.
Absolutely.
So that's our slide 38, and I'll let you handle it. And
Sure. All right. So these key science indicators, the whole idea behind this is that we, as just a population of people that should be concerned about these metrics, establish a set of measurements and metrics that would allow us to have consistent conversations around this topic of unconventional oil and gas development. So just going through the list here, and these are just proposed, right? These are things that you and I have discussed, and no different than when we talk about what a nice warm spring day is like, right? If it's 65 degrees and sunny, we know those metrics of sunshine and 65 degrees have meaning. When we talk about unconventional oil and gas development, those metrics are inherently complex. There's experts like you that have been studying them for entire careers. The volume of data on the database that you mentioned earlier is phenomenal, right? It's a huge volume of data. We need to come up with some meaningful metrics around whether we're green, yellow, or red, right?
Yep.
So looking at these, for example, greenhouse gases linked to unconventional drilling. There's a number for that, right? There's maybe it's difficult to measure, but in the physical world, that's a metric. Geographic mapping of unconventional drilling key science indicators. So looking at individual drilling pads and saying, within all these body of metrics, is that drilling facility red, yellow, or green? Economics, supply chain, energy efficiency. In other words, energy in, energy out. Do you get a good return on investment? Energy consumed and produced, right? How much? Same kind of thing, right?
Yep.
Pollutants, drilling fluid, drilling gases, community health. So instances of asthma and some things that would be maybe more temporary to more persistent issues of contaminated wells and persistent health issues that could come from that. The pollution contamination rate, just how aggressive is the pollution going into the atmosphere and into the water supplies? Contamination, what defines contamination? What are we measuring? Making sure those units are defined. Waste reuse efficacy, making sure that when we're going through and processing this wastewater and all the materials that go into these wells, how efficient are we at reclaiming the water and the sand and other materials that went into the initial extraction of the natural gas? Impact on broader natural systems, key greenhouse gases. All of these, and not to go through the list and continue to bore people, but Tony, with your background and your expertise in this whole realm, is the industry coming to terms with consistent, universally identifiable metrics, much like we can say a nice spring day is measured at 65 degrees and sunny? Does the industry have a good handle on that we could do better communication to the broader public about whether this whole area of oil and gas extraction is red, yellow, or green? You know, like there should be some scoring, right? Like when I look at Western Pennsylvania, is that a red, yellow, or green territory?
I would really
relative to these or other metrics that may define it.
I would like to answer in the affirmative, but I will not. I cannot. I should not. Because regularization, normalization of behavior of the oil and gas industry right now is anathema to human health. You can't have it both ways. You can't have a vibrant, expanding, growing oil and gas industry at the same time you are countering climate change. One is the cause of the other. You can have one or you can have the other. You can either do what you can, you personally, you in your community, you as a voter, you as a taxpayer, do what you can to fight climate change, or you can invest in Exxon.
Well, and that's the other thing too about that whole data set that would go into saying this is a successful operation. This is something that's benefiting local economies. Look, we got jobs that are created, as well as that larger data set that talks about human health, waste storage. Where do we store this stuff? It's almost it's disorienting and exhausting to think about the fact that it's easy and politically easy to sell the benefit of something with a narrow set of metrics that you're measuring. When you look at the broader set of metrics, and that's what seems to be elusive, right? We can't really wrap our heads around the totality of red, yellow, green measurements that would allow people to say, oh, sure, short term, this year, next year, maybe investing in an oil or gas company that is doing this type of work would produce good beneficial results. It almost seems like this larger data set needs to be part of that that financial statement, right? Or the investment portfolio to say, yeah, these things are happening, but the 20 or 30 metrics around how this process is working, it's either good or it's not good. Are those metrics being dealt with and refined within the professional community of not only environmentalists, but industry experts? Because I would imagine a lot of these companies would like to also get ahead of this to make sure that when they're looking at how good or bad things are going, they know if they have well accidents, they know if they have spills, but it's such a more complex discussion that I think it warrants normalization of, like I said, is it a sunny day? Is it warm out? Do we think this is good? Any thoughts on that, Tony?
I tried to express my thoughts a few minutes ago. There is no sunny day.
Gotcha.
There is no sunny day. We can go back and show that chart from the paper in 2012 that predicted our climate future. Now, your viewers might say, well, it's wrong. I don't believe that science. But that's the consensus of the scientific community. That plot has been updated again and again and again over the last 7 years, and it just keeps getting worse. So if you believe that, and if you believe that 1.5 degrees centigrade or 2 degrees centigrade mean very, very, very bad things for all 7.8 billion humans on the face of the earth, then you have no choice but to look at all these key science indicators that are directly related to oil and gas production and say, why should we normalize any of them? We should be shutting it down. We should be as quickly as possible decreasing the production of fossil fuels. I didn't say shutting them down immediately. Can't do that. We're not ready completely. But we should have started 20 years ago, or at least we should have started 10 years ago to read the climate writing on the wall.
Right. And just to jump ahead to slide 39 then, and again, trying to be fair to all angles of the discussion, the positives of unconventional oil and gas development. Local jobs absolutely boost local economies. We've seen this in towns. Now there's been the booms and the busts. But yeah, you can have some increase in local economic activity. Increased tax revenue to improve local services and education. Sure. Cheaper fuel costs for the United States. We're a net exporter, right? National security improved by energy independence. Those are all easily measurable. And again, they belong in the broader set of key science indicators that examines whether this is a good or a bad thing. Some negatives, natural systems that provide clean water. It took millions of years to form. Once they're destroyed, they're gone forever. So My background with environmental engineering at Penn State, I studied groundwater remediation. It's very difficult to do, if not impossible. The hidden cost to maintain and repair transportation infrastructure through increased taxes, not included as cost to the oil and gas industry. It's easy to make money and then have local communities reinvest the money they made by working for the extraction of this fuel just to put it back into the infrastructure.
Yeah.
That should be measured. Cost to clean up contamination, environmental impacts today and in the future. Mineral rights, not confined to a self-contained place and time. I find it fascinating that people can sell mineral rights. They're not going to be around 100 or 200 years from now when you can't drink the water on the property. Or maybe 10 or 15 years from now when you can't, or maybe tomorrow, who knows? Quality of human life is reduced. Air and water contamination, those are absolute negatives. Increases in illness, cancer, and death near drilling sites. Human and animal health far from the original drilling site, either immediate or delayed. Jumping ahead to slide 40 here. What are some ways to protect against the negative impacts? We can do some of these things that we talked about with the encasements, storage pond lining and things like that. But how long will these things really last?
And
slide 41.
Jeff, and what's more, if you do those things, you're just being an enabler. You're putting a Band-Aid on cancer.
And that's the thing, is that when those metrics around these things like storage pond lining, you can have a metrics around, like, how long does that last? How effective is it? What's the failure rate? Those are things that need to be measured so that the data is out there for people to understand. To your point, people will say those are good things and ways to make it safer and better, but it's the time horizon or the scope and the measurement seems to be missing in many cases. Safer alternatives, we talked about it. Traditional oil could actually be a bit safer, right? Traditional natural gas, solar, wind, hydro, redesigning systems to use less energy. I'm a big fan of that. Give people tax incentives to live closer to where they work. Try to get supply chains for goods and services closer to where they're manufactured. Have people, I don't know, hang out in a community and be a part of a larger initiative locally rather than try to distribute things globally. Conservation. All good things that would make this a lot easier and better for us to try to get away from this whole fossil fuel approach.
Let me just add, Jeff, on these safer alternatives. I'm a realist. I'm a pragmatist. I'm an engineer. We have nearly a million producing oil and gas wells in the United States. Most of them are traditional, conventional oil and gas wells. The vast majority of them are. If we were today to figure out a political and socially and economically acceptable way of slowing down the drilling of new wells over, say, a 5 or 10 year period, so that we could gradually ramp down oil and gas production while we're ramping up solar and wind, which, as you know, are growing rapidly. They started at a very small level, but they're growing exponentially. If we could do that, then we could bend the curve. I'm not saying kill the oil and gas industry, send them all to hell, put them all in jail. No, that's absurd. Okay. Right. But we already have 1 million producing wells. We don't need any more if we had a plan for that transition on a national scale, or at least in some of the larger states where there's a lot of population and a lot of demand for fossil fuels, like my state and your state. But we don't have that national plan. There is no national energy plan. Certainly with the situation in Washington right now, any national energy plan which is based on a transition to renewable energy has no hope of ever seeing the light of day, right? That plan would never be even written up. But that's what the science says we have to do. I can sit here and shout and scream and say, believe me or not, and most of your viewers hopefully will believe me. Many won't. They'll just deny the science. Somehow magic will occur. The heavens will not fall. Well, it is what it is. It's certainly important. If I'm going to be realistic about the future, your viewers need to be realistic about the future, and they need to come to grips personally with the fact that they're participating. They're participating in the transition or not. They can choose to keep demanding fossil fuels for their car, for their home, for their business, or they can choose to decrease that demand or eliminate it over some period of years and increase the demand for renewables.
Yeah, and look,
it's the only way it's going to get done. You know, the government isn't. The American people are never going to allow the government to come into their homes and force them to turn off their gas stove. They're never going to allow the government to come into their garage and say you can no longer drive your V8 SUV that gets 12 miles per gallon. They're not going to allow that. But what the government should be expecting is that each of us operating in a capitalist society, knowledgeable about climate change and the impact it's going to have on you and your kids and your grandkids, would be doing that voluntarily.
Right. To that point, looking at slide 41, solar, wind, hydro, the idea that we would have electricity generated in sustainable ways, those are also important key science indicators. And the reason why I've got that slide there is that the metrics around that need to be understood and standardized. You know, looking at slide 42, for example, just some examples of potential key science indicators and potentially some numbers. But you can see there, like between vertical and horizontal drilling, these are numbers, right? And there should be a per well set of data that can easily be looked at high level down to the well itself. You know, I think of a lot of these, there's Frac Tracker, which is a great website. But even within that website, I feel like more could be done to get those universal metrics established so you can literally, from a high level view, see those key metrics right down to the neighborhood. And again, slide 42 here, just showing some examples of what some of those metrics may look like.
And these
especially
these
comparing conventional and unconventional.
These metrics are changing. You know, this slide was created in 2012, that table. I'm
right.
It came from the Paleontological Research Institute here in Ithaca, New York. Back then they were saying, 2 to 9 million gallons of water required. I just showed you data that says no, it's now the average is 12 to 15 million gallons.
Right.
So the metrics keep changing, but they keep changing in the wrong direction.
Well, I was going to say, like water required per well, that's a metric, and there should be a map that anyone can go to, and you can look across a geographic area and see these metrics and understand, are they getting worse? Just how the industry and the broader population, it's so complex. There's so much information. I think the real science that's ahead of us is distilling this down so that it's tangible and consistent in definition.
Yep.
Slide 43 again, just to look at that website that you had mentioned.
Yep.
Over 1,600 articles at the time this slide was put together. What are we up to? 1,900 now?
Last time I looked, it was about 1,700.
Or 1,700. I'm sorry. Yeah. And again, great articles, a huge body of information to get the metrics out of these studies and get them into geographically relevant plots so that we can see, are we green, yellow, or red? That's the whole idea around these key science indicators. Fractracker.org, I mentioned that before. That's a great site. A lot of really good information out there.
Fantastic source of information.
Yeah, absolutely. And then just to kind of wrap it up here, actions. Existing team of scientists to establish an industry baseline of metrics. Again, these are just open thoughts. Kind of like an open standards organization. Certification for data gathering and reporting. Similar to how we certify food as organic. There should be measures that this is good and healthy and this is out of parameter. This is unhealthy. Some kind of an independent body that would maintain data quality standards. Consistent reporting methods. Reporting output that is easily understood by the public and lawmakers. That's probably the most important. So that when we're establishing policies for our local and state and national policies, we're working with data that makes sense and we can all look at it together and say, it's good, or, oh my gosh, it's not good. Validating the validators. Ways to improve that the data is correct and not influenced by conflicts of interest on all sides, right? We've heard, that guy fudged a number and that report had some redactions or whatever. The point here on that bullet point is making sure the data is trustworthy and accurate so that when we're measuring things like all the key science indicators that we talked about, that we're not misled or that we're not fooling ourselves or that there's not bad actors from any side of the debate. The data has got to be trustworthy. I can't say when I'm building a house that wall is 9 or 10 feet and then, show up and try to attach something to it and realize it's only 7 feet. Measurements in physics matter, and the fact that this is so complex and so intangible makes it all the more important that the data is valid. That there's no doubt about it. So Tony, that wraps it up. I'll just flip through these last 2 slides here to get the citations and credits. And any closing comments. By the way, I wanted to say my sincerest thanks as I've pursued this experiment over a very long time. I appreciate your patience. I'm very grateful for your friendship and just the time that we spent together working on this. I can't thank you enough. It's meant a whole lot to me.
Jeff, it's been a real pleasure working with you. We've been through hell and high water at various times for technological challenges to get this off with a high quality show. And the last comment I would make is I can't sit here in all honesty and preach at your viewers without having data. Like you just said, you have to have data that's believable. So my wife and I, we walk the walk. The house I'm sitting in right now, I'm in my home office. This is an all-electric house. We don't have gas coming into this house. This house produces far more electricity than it uses. It's better than net zero.
Oh, fantastic.
We drive an electric car. And when we need to fill the battery, we fill it up in our garage from our rooftop. So, not everybody can do as much as we've done. I don't expect that. Again, I'm a pragmatist. I'm a realist. We've done, and we continue to do everything we can so that when I preach, like we've been doing tonight, nobody can accuse me of being hypocritical. But I understand that not everybody can go as far as we've gone or as fast as we've gone. But we're all citizens of the earth. We're in this together. It's the only earth we have. It's our lifeboat in the cosmos. And I hope that everybody eventually figures out what they can do and do it as quickly as they can. So again, thank you very much, Jeff. It's been a pleasure. Sorry I took so much time away from your family over the last year and a half.
No.
Good night.
Good night. Thanks very much, Tony. Hey, check out thescienceprogram.com for the latest on key science indicators. If you have any ideas for future shows, you can submit them there. Also, if you're an expert on a particular topic, you can learn how to become a guest at thescienceprogram.com. Thanks for watching.